problems of finding out sufficient statistics for some distributions. So have you solved those problems? Has anybody solved the problems? Then you can tell me. So let me write those statements here. So first problem that I had given was for the gamma distribution with parameters, say, suppose I write P alpha. Okay. So have you solved this problem? Here there are three cases. In one case, P is known, alpha is unknown. In another one, P is unknown and alpha is known, and in another one, both are unknown. So can anybody answer this question? Let me ask some of the students here. Venkat Sai. Have you solved this problem? Priyanshu?
Yes, sir.
Okay, tell me the thing. So
Sir,
let us write down
tried,
the
but
cases.
I didn't get the answer.
Oh, you have not got the answer.
Yes.
Priyanshi? Priyanshi? Vijay Kumar? Are you there? Are you just joined there?
Sir, I too tried, sir, but I didn't.
Anybody who has got the answer? Saurabh Jaiswal?
Yes, sir. Am I audible?
Yes.
Sir, I tried, but I haven't got the answer.
Now, what is the difficulty? What is the problem? I mean, what is the difficulty? Because this is straightforward method. I have already explained several exercises. So what is the problem? Yeah, tell me the problem, Saurabh. What is the problem? Yes. What is the problem? Hello?
Yes, sir.
What is the problem?
Sir, I'm just telling.
So I'm writing the first case, P is known and alpha is unknown. Then what is the sufficient statistics here? Hemant Rao?
So
Yes.
I haven't up to try it.
See, the problems that I am giving, actually, you people have to solve it. I mean, if you are not solving, then you will not be able to understand anything. And in the exam also, you will not be able to solve any problem. Okay, I mean, I think you people have not tried at all. I mean, this is not acceptable actually. So let me write here the joined PDF. Here you have to write So if I am taking P to be known and alpha to be unknown, in that case, I will write the parameter only as alpha here. Okay, so that is the product I is equal to 1 to n f xi alpha. So that is equal to product I is equal to 1 to n. Now you write down the distribution of gamma with parameter p and alpha. So that is alpha to the power p by gamma p e to the power minus alpha x to the power p minus 1. So here I will put xi here. Here xi's are all positive. So this becomes alpha to the power np divided by gamma p to the power n e to the power minus alpha sigma xi product xi to the power p minus 1. So here parameter is alpha. So if you look at the factorization, then this part I can put as g of alpha and sigma xi, and this part does not involve parameter, so this is hx. Okay. So by factorization theorem, then sigma xi is sufficient for the family of gamma distributions. Generally, we are writing P first and then alpha. So I will write like that. P is known and alpha is positive. Did you understand this? Is the exercise clear? If you look at the same thing, and if I take P to be unknown and alpha to be known, then only this arrangement has to be written in a different way. That's all. So let us take the case 2. Alpha is known and P is unknown. Then the joint PDF is so it is alpha to the power np. The way I wrote here, I will write the same thing here. Alpha to the power np by gamma p to the power n e to the power minus alpha sigma xi product xi to the power p minus 1. Since here now p is the unknown thing, then this part I will put together and this part will go into hx. So this part will come into g of p and product xi and into hx. So by factorization theorem, now you will get product of xi as the product xi is sufficient. For the family of gamma distributions. So if the parameter is changing, then the sufficient statistic is also changing. And now if both the parameters are unknown, then the joint distribution will be functions of p and alpha. And this term that we have got here, the whole thing I will write as a function of alpha to the power np by gamma p to the power n e to the power minus alpha sigma xi product xi to the power p minus 1. So this whole thing we can consider as a function of g of p alpha sigma xi product xi, and hx you can take to be simply 1 here, because all the terms I am putting in g. So sigma xi and product of xi is sufficient when both the parameters are unknown. Where p is positive and alpha is positive. So sufficiency is completely a property of the family of distributions. That means what are the parameters that we are considering? Based on that only sufficiency has any significance. Because what is the purpose of sufficiency? That is to draw the inferences on the required parameter. So in this particular case, for example, if there is an inference problem on alpha, then sigma xi will be useful, and if there is an inference problem on p, then product of xi is useful. So of course, when the jointly p and alpha both are the parameters, and then there is an inference problem, then you will consider the inference based on sigma xi and product xi. We have already given the Rao-Blackwell theorem, which says that if you have unbiased estimation problem, then you should base your estimators on the sufficient statistics. So is this exercise clear to all of you? Is the exercise clear?
Yes, sir.
So now let me ask about the another problem, that is about the beta distribution, okay, which I had also given earlier in the last class. So let me expect the solution from you now. So we have a random sample from a beta distribution with parameters say alpha and beta. Okay, you find out the sufficient statistics for the 3 cases where alpha may be unknown, beta may be known, and otherwise, or both are unknown. So since you have not solved it, please solve it now and tell me the solution. Okay, beta distribution with parameters alpha and beta. Okay. So I will give you a few minutes time, maybe 2-3 minutes. You please take it and tell me the solution. Okay. Okay, so I expect that you please tell me the solutions. Okay. in the three cases. Okay, so let me ask someone. So has anybody got the solutions now?
So first one is pi of xi, and second one is pi of 1 minus xi, and third one is both of these.
Pi means product.
Product.
Product of xi in the first case. In the second case? In the second case? Yes?
Product of 1 minus x.
Product of 1 minus xi. And in the third case?
Both product of x.
So in the third case, it is the product of xi and product of 1 minus xi. So I think now you have understood the procedure. So let me ask the third one now. Let us consider Pareto distribution. Okay. If you are not knowing the distribution of Pareto, let me write down the form of the distribution here. So it is alpha to the power beta x to the power beta plus 1 into beta x greater than alpha, where alpha and beta both are positive. Okay, so this is Pareto distribution with 2 parameters. I mean, Pareto distribution, of course, is one of the very, very important distributions because it is basically used as the income distribution. Like what we consider here, that suppose this is the starting point alpha. At alpha, the value of this is beta by alpha. So some value, for example, thereafter it will decrease. Okay, it goes like this. So basically the interpretation is that there are few people with very high income and there are most number of the people are in the lower income group. So that is the thing, that there is a lot of weight here. At the higher side, the weight is less. So less number of people get more income and more number of people get less income. So that is the basically Pareto law or Pareto rule, and it is also called 80-20 rule or sometimes 70-30 rule. That means 20% of the people have 80% of the resources, 80% of the people have 20% of the resources, and that kind of things are there. So now, so this is of course one of the very useful distributions in statistical inference. So now let me look at this one and tell me the sufficient statistics. So beta is known, alpha is unknown, and okay, so again I am giving you 2-3 minutes time. Please look at it and then tell me the solutions. Yeah, okay, so now tell me what are the sufficient statistics in each of the cases. So anybody who has done it? If alpha is unknown and beta is known, then what is the sufficient statistics here?
Sir, is it product xi?
Okay, is that enough or anything else? Is that enough? Product xi?
Sir, I'm still doing it.
Okay. Anybody else? Jay Kumar? Shashank? Venkat Naidu? Anushka?
So beta unknown, product of xi.
If beta is unknown, then it is product of xi. Okay. Then alpha is unknown.
The minimum of the distributions.
Minimum of the sample. And the third case, when both are unknown.
Both minimum and product.
So later on, you will see that when we are doing the desirable statistical inference, that means in terms of maximum likelihood estimation or finding out minimum variance and bias estimators, then this information will be precisely used there. Okay, so we will look into that thing afterwards. So firstly, let me now also connect this concept of sufficiency, because there is another term which I introduced earlier, that is information. So they are English language terms, but here we have used the meaning in the literal sense. That means if I say it has this information or information in the sample, then it means that we are able to say something about the parameter based on that. So similarly, if I say this information is sufficient or this statistic is sufficient, that means the information which is there in the sufficient statistics is enough for the statistical inference purpose. So let me now do it a formal theoretical equivalence of this concept here. Let me just use the basic terminology here. So suppose I say X is having a distribution fx theta. So I'm not bothered too much about here whether X is X1, X2, Xn, etc. I'm just writing X. Okay. So the Fisher information that I defined, if you remember the definition, that was expectation of del by del theta log of fx theta whole square. Okay. Now, of course, we should have regularity conditions are satisfied. Okay. Otherwise, we cannot consider this derivative, etc. Okay. So if I am considering T to be any statistic, so T is a function of X, so it will have some distribution. We can find it out. So actually we are using fx theta as a general term. So it could be discrete or continuous. So PDF or PMF. Let me call it phi t theta. Okay, just I am changing the name of the distribution of this. And then the Fisher information in T will be I T theta, that is expectation of del by del theta log of phi t theta whole square. Again, of course, regularity conditions must be holding, otherwise this type of statements cannot written. Okay. Then we have the following theorem. In general, information in the sample is always greater than or equal to information in a statistic. Okay. In particular, information in the sample is equal to the information in the statistic if and only if T is sufficient. So this is one of the very powerful statements here, that in general, if I have the data x1, x2, xn, and I am considering only some function of x1, x2, xn, then in general I am losing the information. Okay, because the information contained in certain functions will not be equal to the information in the full sample. However, if the statistic is sufficient, then it will have exactly the same amount of information as in the whole sample. And this allows us to discard the full sample and we can keep track of only the sufficient statistics. Is the statement understandable and clear to all of you? Is the statement understandable to you? Okay, I'm not hearing any answer from anybody. Is the statement clear?
Yes, sir, it's clear.
Okay. So let me explain through the Poisson example. Okay. So I consider the statistics T1 say x1, T2 is say x1 plus x2, and T3 is say sigma xi, I is equal to 1 to n. Okay, I am taking these three here. If this is a random sample from Poisson lambda distribution, then we know the distributions of T2. T2 will follow Poisson 2 lambda, T3 will follow Poisson n lambda. Okay, so let us look at the information here. First of all, we will calculate the information in the full sample. Okay. So let me consider the form of the probability mass function here. It is e to the power minus lambda, lambda to the power x by x factorial. So log of fx lambda, that is equal to minus lambda plus x log lambda minus log of product x factorial. So if we differentiate this with respect to lambda, these things we have done in the maximum likelihood estimation, etc. also. So the calculations are similar kind of thing. Only thing is now I am writing for one term, and otherwise we could write for n terms also. But since information can be just edited, so there is no need to calculate for the entire thing. I mean, it is enough to calculate for one. So if I consider this that is equal to expectation of x by lambda minus 1 square, that is expectation of x minus lambda square by lambda square, then it is the variance of the Poisson distribution is lambda, so lambda by lambda square, that is 1 by lambda. So now we are able to get the information for all the terms here. So information in the sample that is Ix lambda, that will become simply n by lambda, and this one which we have calculated, it is for one term, so information in T1 is 1 by lambda. So obviously you can see information in the full sample is greater than this. So information in the sample is greater than information in one observation. Okay. Similarly, if I consider information in T2, T2 is Poisson 2 lambda. So this is by the same logic. If we are writing down what will be the information in this, that will become 2 by lambda. So this is again less than n by lambda. Whereas if I am considering information in x1 plus x2 plus xn, that is n by lambda. So that is equal to n by lambda. That is the information in the full sample. So by the above theorem, T3 is equal to sigma xi is sufficient. So this is the relationship between sufficiency and information here. Is the example clear to all of you?
Yes, sir.
Okay. So next See, I am saying information is additive, etc. So let me write it formally also. Okay. This is an additive measure. Okay. That means let x and y be independent random variables with PDFs or PMFs. Okay. Say fx theta and let me put fx theta, f1x theta and f2. Okay. But parameter I am taking to be the same, theta. Okay. Then we define the information in x plus y. Then that is information in x plus information in y. Proof is just based on the expression of the information. If you remember, I have given alternative expression for the Fisher's information. This is the definition of the information in x, but I had written an alternative expression for this, that is minus of expectation del 2 by del theta 2 log of f1 x theta. When I was doing the Rao-Kramer lower bound, then I have given this alternative expression there. Similarly, the information in y is minus expectation del 2 by del theta 2 log of f2 y theta square. So if I am looking at the complete information in x and y, actually I should not write here x plus y, rather I should write x comma y. This one, let me modify the statement here, because it is not addition, it is full sample. So the information in the all observations is equal to the sum of individual informations. So I mentioned it and used it in an earlier statement. So let me write a formal proof of this. So the joint probability density function of x and y, so that is gxy theta, that's f1 x theta into f2 y theta, because the random variables are independent. So the product of the densities is equal to the joint density. Okay, so if I take log of this, yes,
The alternative form of the Fisher information, that del square by del theta square. There
okay,
should
second
not
one
be-
I have put a mistake here. Yeah, there is a mistake here. Yeah, there is no square here. Yeah. Thank you for pointing out. Yeah, there is no square here. Yeah. So if I take log of this, then this is log of f1 x theta in plus log of f2 y theta. So if I consider second order derivative, that is nothing but sum of sum of the second order derivatives here. So if you take expectations on both the sides, you get the required relation. we get that the information in xy is equal to the information in x plus information in y. So this Fisher's information measure is additive, which is a very useful property basically, because a lot of things can be done through that. Okay. So let me give you one exercise here. Suppose I take a random sample from normal distribution with mean mu and variance I am taking to be 1 here, okay, where mu is any real number, okay. Find okay, I am just putting these two exercises, so please find out and tell me the solutions. I am giving you 2-3 minutes time to evaluate this.
Can you drag a bit up?
Hello, what is the question?
So, not a question, sir. Like I have to note a small point. Can you drag a bit up? Thank you, sir.
Yeah, okay. So could anybody do this problem? What is the Fisher information in T1? What is the Fisher information in T2? What is the Fisher information in T3? And what is the Fisher information in the sample? Of course, that problem we have already done, but anyway, I'm repeating that thing here. Because in Rao-Kramer lower bound, we have already calculated that. Yes. Anybody is able to do this? Spandan Haldar. Spandan Haldar. Sajida Kausar. Yeah. Can you tell me the information in T1, T2, T3?
I didn't get
Yes, anybody else? Likhit Reddy.
Yes.
So for example, what is the information in the full sample here? So I write down the distribution of one observation here. Then log of fx mu, that is minus half log 2 pi minus 1 by 2 x minus mu square. So we consider derivative of this with respect to mu. That is x minus mu. So expectation of del log f by del mu square, that is equal to expectation of x minus mu square. That is the variance of x, because expectation of x is equal to mu. So here variance is 1. So the Fisher information in one observation is only 1. Okay. So Fisher information in sample will be in the sample that, let me write Ix mu, that is equal to n here. Okay. If I want to calculate the Fisher information in T1, T1 is x1 minus x2 here. So if I consider T1, that is x1 minus x2, what is the distribution of T1? That is normal 0, 2, because they are independent and identically distributed random variables. So linearity property of the normal distribution can be used. So x1 minus x2 will have normal distribution with mean 0 and variance will become 1 plus 1, that is 2. So the distribution of this does not have, if I write down the distribution of density of T1 is free from mu. So if you differentiate with respect to mu, you will get 0 there, isn't it? So information in T1 is simply 0. So basically x1 minus x2 does not give any information on mu. Okay. Is this point clear?
Yes, sir.
If I look at T2, that is sigma xi, that is normal n mu n. So what is the information in T2? What is the information in T2?
N.
It will be n. So you can see that this information is same as the information in the sample. So T, that is T2 is sufficient. Of course, we have proved it otherwise also using the factorization theorem, but here you can see the actual role of information here. What about T3? What is the information of T3? That is the sample variance here. 1 by n minus 1 sigma xi minus x bar square. How much information it gives to the about the sample? Yes. How much information this T3 has?
2n.
Okay, so what is the, how did you calculate it? How did you calculate it? Yeah. Can you tell me the method of your solution? How did you get 2n there? Now, why is it 2n? Actually, if I consider n minus 1 s square by sigma square, which is 1, that follows chi-square distribution on n minus 1 degrees of freedom, which is free from mu. So if you differentiate log of the density with respect to mu, you will get 0. So therefore, the information is 0 here. The sample variance does not contain any information about the parameter mu in this case. Okay. There is no information using this. Did you understand this? It is not 2n. because the density of S square will be free from mu. So if you take log of that and differentiate with respect to mu, you will get 0. So the information in T3 will be simply 0. So actually here sigma xi or x bar, that is sufficient statistic in this normal distribution problem when mean is unknown. Here variance I have taken to be known. Okay, is this discussion clear to all of you? The relationship between sufficiency and information. Is it clear?
Yes, sir.
Now in a given problem, there can be several sufficient statistics. In fact, I have already told in the beginning that the full sample is always sufficient. And then any function, if I am writing by using factorization theorem. So I am writing g of, say for example, x1 plus x2 plus xn theta. But x1 plus x2 plus xn itself is a function of many things. For example, I can consider x1 plus x2 and then x3 plus x4 plus x5 plus xn. Okay, because if t is a function of u, then if t is sufficient, then u is also sufficient. Okay, so since in a given problem there are many we should look for the one which leads to maximum reduction of data. For example, if I am saying sigma xi, then I am keeping only single number. Like in earlier cases, you have seen like minimum of all the observations or product of all the observations, etc. Various kind of things you have seen. So if that is enough, then why should I keep something else? I should be interested the maximum reduction of data. Okay, so by observation you can say here, for example, sigma xi or product xi, in those exercises we can see that thing. But there can be more difficult cases. For example, I have given double exponential distribution. In the double exponential distribution, we were not able to reduce anything. So I said, okay, x1, x2, xn ordered one I will consider to be sufficient statistics. Okay, so the question is that how did I get that thing? Okay, that how did I say x1, x2, xn ordered one I will take, since I am not able to reduce any further. Okay, so this concept has been formalized in statistics. Okay, so a concept of minimal sufficiency. Okay. So I will introduce through a little bit of algebraic description, but I think this much algebra you know. Okay. So partition of a space, say X, is a collection of sets, say EI, subsets of X, such that they are disjoint and their union is equal to the full space. Union of EI is equal to X and EI intersection EJ is equal to phi for all I not equal to J. So the sets EIs, they are called partition sets. So if I am considering a statistic T, so like if I say X, then X square or sigma Xi, etc. So for example, in a problem where I have n sample points x1, x2, xn, suppose in the normal distribution case, then each of the xi's can be from minus infinity to plus infinity. That means they will belong to the real line. So if I consider x1, x2, xn, it will belong to the n-dimensional Euclidean space. Now if I am considering x bar or sigma xi, then that is a real valued. So all the points x1, x2, xn which lead to the same sigma xi, they belong to one partition set. Okay. So in general, if I have a function, say from x into y, here it is basically statistic. Okay. From domain x into range y, then the partition induced by the partition of x, okay, induced by T is the collection of sets I can call it something like Ty. It is the set of all those points x such that Tx is equal to y. Okay, so this leads to a partition. So let us just understand it through some very simple examples. This is some very basic algebra, so this should not be difficult. So suppose I take x to be the real line and I take function Tx to be x square. Okay, then what is your range? That is 0 to infinity, and Ty is nothing but minus root y plus root y for all y positive, and for 0 it is 0 only. So then the collection T0 and Ty for y greater than 0 is a partition of x induced by Tx is equal to x square. I hope it is clear.
Yes, sir.
So similarly, we can just consider, say, suppose I take x is equal to Rn and say Tx is equal to sigma xi I is equal to 1 to n, where each xi belongs to R. All right. Basically, we can write it in this fashion rather than writing like this. I can write it as x is equal to x1, x2, xn belonging to Rn. Okay. Then what kind of thing I will be getting? So I can write here what is the range of this? That is again R, because sum of all the numbers in the Euclidean spaces will be real numbers. So if I consider, say, Ty, it is the set of all the x's in Rn such that sigma xi is equal to y. So then Ty, y belonging to R is a partition of X. So n-dimensional Euclidean space has been partitioned like this. Partition of X induced by T. So a partition is induced by a function. However, several functions may induce the same partition. It is not unique. Okay. So there is not a one-to-one correspondence. But only thing is that if I have T1 and T2, two functions which induce the same partition, then we can say that from one function as a remark here. If two functions T1 and T2 induce the same partition, then they must be one-to-one functions of each other. Let me give some exercise here. Okay. Suppose I consider X is the set of all English letters. Okay. And T of the letter. Okay. T of, let me put because we are already using this one. So I'll put T alpha is equal to 0 if alpha is a vowel, and T alpha is equal to say 1 if alpha is a consonant. Okay. Then what is the partition here? Then T induces the partition the set of vowels. So I can use some notation here. V is the set of vowels and C is the set of consonants. Let me take another example here. Say X is the set of certain colors, say red, white, green, blue, yellow, and violet. Okay. And I define, say, T1 of red and T1 of white. It is equal to 1. And then T1 of green and T1 of blue, that is equal to, say, 2. And T1 of yellow and T1 of violet, that is equal to 3. And then I define T2 to be T1 minus 2 whole square. Okay. So first of all, let us look at the partitions induced by T1 and T2. The partition induced by T1, I will call it, say, P1. So it is red and white are in the same set. Green and blue are in the same set. And yellow and violet are in the same set. Okay. Is this clear? Is this clear?
Yes, sir.
Now, what is the partition induced by T2? You see here, when T1 is 1, then T2 will be 1. When T1 is 2, T2 is 0. When T1 is 3, then also T2 is 1. So the partition induced by T2, if I call it P2, then it will have green, blue, that is corresponding to the value 0, and red, white, yellow, and violet. That will come into the another partition set. Okay. Here, if you see the sets of P2, they can be obtained by taking union of the sets of P1. For example, the set green, blue, and yellow, violet, if you take union, you will get the set here. So P2 is said to be a reduction of P1. Okay. We will say that partition P2 is a reduction of partition P1 if each partition set of P2 is a union of some members of P1. So here so is this concept of reduction understandable here? If I say that T1 induces partition P1 and T2 induces partition P2, and if P2 is a reduction of P1, then T2 is a function of T1. Of course, this is if and only if. Now with this concept, now you can consider, because I mentioned the reduction in the context of sufficiency, that is the data reduction. So if we have a sufficient statistic which induces the smallest partition, the most reduced partition, we will call that to be the minimal sufficient statistics. And that would be of interest to us, because in any given statistical inference problem, we would like to reduce the data to the maximum extent such that we do not lose any important information. The measure of information is already available to us. That means among all the sufficient statistics, we will consider that one which has the maximum reduction of the data or the smallest partition. Okay. Is this clear? This statement which I gave just now, that if P2 is reduction of P1, then T2 is a function of T1. Is it clear?
Yes, sir.
So let us go to sufficiency now. The purpose of this discussion was just to introduce the partition sets actually. So some little bit of algebraic concepts are used here. Now let us go back to sufficiency. So let T, that is Tx, be a sufficient statistic. Okay. Then the conditional distribution of X given the partition set X such that Tx is equal to T is independent of the parameter. Because the definition of sufficient statistic was that the conditional distribution of X given T is equal to T is independent of theta. So here Tx is equal to T means it is the partition set. So in terms of set theory, if I want to just modify my statement, it will be like this. Okay. Now this is useful for actually getting to the minimal sufficiency. So let me explain firstly through some example, and then we will go to the actual definition here. Suppose my parameter space has 3 points, theta 1, theta 2, theta 3. And suppose my random variable also takes only 3 values, x1, x2, x3. So this is, I'm just taking a special case of a discrete distribution with a finite parameter space. Suppose the probability mass function of X is given by, okay, so P theta 1 X is equal to x1. Suppose this is 0.1. P theta 1 X is equal to x2. Suppose this is 0.2. And P theta 3 X is equal to x3 is equal to say 0.7. Okay. So when theta is equal to theta 1, the distribution of x is the probabilities corresponding to x1, x2, x3 are 0.1, 0.2, 0.7. Suppose theta is equal to theta 2, then the probability distribution is 0.2, 0.4 and 0.4. When theta is equal to theta 3 is the true value, then it is 0.3, 0.6 and 0.1 here. Okay. Let me consider here partition as follows. It is consisting of two sets, say x1, x2 I put in the one block and x3 I put in the second block. Let us look at the conditional distribution of x given these two. Okay. We will find conditional distribution of x given these partition sets. Okay, that is this one and this one. So let us consider first one. So probability of x is equal to x1 at theta 1 given x is equal to x1 or x is equal to x2. First partition set I am taking, that is having x1, x2. So by the definition of the conditional probability, it is nothing but probability of this intersection this, but this is a superset of this. So in the numerator, I will have only probability of x equal to x1 given x equal to x1 plus probability x equal to x2. So this is 0.1 divided by 0.1 divided by 0.1 plus 0.2, that is 1 by 3. Okay. Similarly, if I take theta 2 here, probability of x is equal to x1 given x equal to x2 or x equal to, sorry, x1 or x equal to x2. When it is theta 2, then by the same logic, it is 0.2 by 0.2 plus 0.4, that is again 1 by 3. And the third one, that is p theta 3, x equal to x1 given x equal to x1 or x equal to x2, that is 0.3 divided by 0.3 plus 0.6, that is 1 by 3. Now let us look at second value, because this is x equal to x1. Conditional distribution or conditional probabilities of x equal to x1 given the first partition set I have calculated. Let us look at other one. So probability of x is equal to x2 given x equal to x1 or x equal to x2. Again, the same type of calculations will be there. It is 0.2 by 0.1 plus 0.2, that is 2 by 3. And then you have probability theta 2 x equal to x2 given x equal to x1 or x equal to x2, that is 0.4 by 0.2 plus 0.4, that is 2 by 3. And p theta 2 x is equal to x2, sorry, x3, x equal to x2 given x equal to x1 r x equal to x2, that is point and the third one will be 0.6 divided by 0.3 plus 0.6, that is again 2 by 3. You can notice here what I am trying to conclude here, that these values are independent of theta, because irrespective of whether it is theta 1, theta 2 or theta 3, the probabilities are the same. Let us look at the next one, that is probability of theta 1 x equal to x3 given x equal to x1 or x equal to x2. Obviously this is 0 because this set and this set are disjoint, so this is 0, and this is true for all i's, I is equal to 1, 2, 3, so I don't have to write the statement repeatedly. Let us now consider probability of theta 1 x equal to x1 given the second partition set. Again this will be 0 because this set and this set are disjoint. So for theta is equal to 1, theta 1, theta 2, theta 3, in all the cases this is going to be so for I is equal to 1, 2, 3, this is going to be 0. Similarly, if I take probability of x equal to x2 given x equal to x3, that is also going to be 0 for I is equal to 1, 2, 3. And if I consider probability of x equal to x3 given x equal to x3, that is going to be 1 for all I is equal to 1, 2, 3. So P, that is splitting the sample space into two parts, this is a sufficient partition. So any statistic which puts T1, x1 and x2 in one part and x3 in another part, that means which assigns equal value to x1 and x2, it will be a sufficient partition. So for example, if I define Tx1 is equal to Tx2 is equal to say A and Tx3 is equal to B, then, and A is not B, okay, then T is a sufficient statistic. Okay, is this example clear to you? Because I just wanted to introduce this concept of reduction through partition. Okay. Do you understand this? Did you understand this concept of partition and then introducing the sufficiency through partition actually? Do you understand this?
Sir, can you scroll?
Yeah.
Next.
You can see here that when I am considering probability of x equal to x1 given the first partition set, then irrespective of whether it is theta 1, theta 2 or theta 3, the answer is 1 by 3. When I am considering probability of x equal to x2 given the first partition set, then irrespective of whether it is theta 1, theta 2 or theta 3, the probability is 2 by 3. When I am considering the probability of x equal to x3 given the first partition set, then irrespective of whether it is theta 1, theta 2 or theta 3, the probability is 0. When I am considering probability of x equal to x1 given the second partition set, then for all theta it is 0. The probability of x equal to x2 given the second partition set is 0 for all theta, and the probability of the x equal to x3 given the second partition set is always 1. So in all the cases, we have seen that the probability does not depend upon changing theta 1, theta 2, theta 3. So therefore, this partition is a sufficient partition. So if there is any statistic which I am using which gives x1 and x2 into one set and x3 into another one, then that will be a sufficient statistic. Okay. I hope this is clear.
Yes.
Let me take another here. Suppose I take another partition set. Suppose I take x1 into one part and x2, x3 into another part. Okay. Just for the sake of calculation, I'm putting it here. Let us look at what is the probability of, say, theta 1 x is equal to x2 given, say, x is equal to x2 or x equal to x3. So probability of x equal to x2 and theta 1, that is 0.2 divided by 0.2 plus 0.7, that is 2 by 9. Suppose I consider probability of x equal to x2 given x equal to x2 or x equal to x3 under theta 2, then it is 0.3 divided by 0.4. So that is, sorry, I put it wrongly here. In the second case, it was 0.2, 0.4, yeah. It was 0.4 plus 0.4 and 0.4. That is half. So they are not same. These two are different. Okay. So it depends upon theta. So P star is not a sufficient partition. So I will give the following statement then. A sufficient statistic induces a sufficient partition conversely given a sufficient partition we can define a sufficient statistics. Of course, this is not necessarily unique because several equivalent you can define, but they will be functions of each other. So we can say two statistic T1 and T2 that induce the same partition must be in one-to-one correspondence with each other. So I think this concept is clear to you, the concept of partition induced by a statistic and what is a sufficient statistic and the relationship between a sufficient statistic and sufficient partition. Is that okay? So based on this, then I will consider what is minimal sufficiency. So maybe I will do it in the tomorrow's class because today we have already exhausted. Yeah. So because I did not give any break here, so let me now stop the class. Do you have any questions at this point? Anybody has any questions?
Sir,
Yes.
efficiency characteristics for the Pareto distribution.
Yes. Yes.
I mean, in the beta known, alpha unknown case, how can it be x1?
The second case or first case?
First
This
case,
first
sir.
case. Yeah. Yeah. So if you write down the joint distribution, what it is? Beta to the power n, alpha to the power n beta divided by product of xi to the power beta plus 1. Okay. Into the indicator function of alpha to infinity x1. Okay. Because each xi will be greater than alpha. So this will be 1 if x1 is greater than alpha, the minimum. Now when beta is known, then this part we don't have to bother. This is separate, and only this part I will consider into g of alpha x1. Okay, and this part I will put into hx. So here x1 will be sufficient. Is that okay?
Okay.
Yeah. Is there any other question? Is there any other question? If there is no other question, then I will stop here. And in tomorrow's class, I will introduce the minimal sufficient partition, minimal sufficient statistic, and how to determine that. Okay, because by factorization theorem, we can determine several sufficient statistics, and which one will reduce the maximum. That what is the theoretical idea behind that. So I will do it in tomorrow's class. Okay.